All right, let's get started. Hope you all had a good weekend. So last class, what we were doing is looking at the limits, right? And at the end of class, basically what I was giving you was a graph of a function and asking you to identify, the limit from the left, the limit from the right, right? Okay, and we looked at the left-hand limit, the right-hand limit, and then we said, this is important, but we said that to say that the limit exists on a function, the left and right-hand limits had to be the same. So they had to be coming in from both sides to the same point in order to say that the limit exists. So these were the notations we established. We had the left-hand limit. How do I know this is the left-hand limit? Negative. The little negative right here, right? And then the plus up here is the right-hand limit. And then this limit, what we're saying is if you don't have a plus or minus, that means that this one and this one both exist and they both go to the same place. They both have the same value. So if these two turn out to give you the same answer, then this limit will exist. If the limit, if we don't have a limit, then we say the limit does not exist. And you might see me writing DNE. That's a D. DNE for does not exist. If perhaps the limit doesn't exist. That means like if I ask for a limit here, and you check from the left and the right, and they go to different places, then we would say the limit doesn't exist. All right? All right, so our goal today is to, instead of me give you a graph and have you look at it and see what's happening, all I'm going to give you is the function. I'm not going to give you the graph, and we are actually not going to graph them at all. But we're still going to be able to look at limits. So it may seem strange to you, like how are we going to figure out what a function is doing from the left and from the right if we don't actually have the function to look at? Do you see how that might be problematic? Okay, but we'll do it, all right? And to do it, we need to establish first some things called the limit laws. And these are the things that you can trust as being true. Okay, so we're giving these to you like rules, all right? And you're allowed to use these rules. By the way, I'm still in 10.1, and I do not believe I'm going to go into the next section today. I think I'm going to spend all my time in this section. The next section that we're going to do is called continuity. It's not vitally important to the course, so we can jump through that one pretty quick. So I'm not afraid about being a little behind. We'll be able to catch up. So here are the limit laws, and these are on page 494 of your textbook, and you'll see them right in the middle of the page. They call it Theorem 2, if you're referencing your book. All right, so I want to just go through these, all right? And it's important that we just talk about them rather than just, oh yeah, there they are. So the first thing it says here is assume that the limit, they're using c, okay? The limit as x approaches c of some function f of x equals L, and the limit as x approaches c of some other function g of x equals m. Okay, so the limit laws that I'm going to give you start out by saying assume that this is given. Okay, so what does this mean? This means that we have some graph of some function f, all right? And I don't know what it looks like, but some graph here. And it says that as we approach c, so let's just pick a value c, that as we approach this point from the left and from the right, that they go to the same point, and that the answer is L. That means that the height of this function is L. So this is by stating this as being true to start with, they are telling us that the function goes to the same place from both sides, all right? And then they say, all right, well then you've got this other function, not necessarily the same one, some function g, where if you go to the same value c, that again, from the left and from the right, they go to the same place, but this time it's m, all right? So you got these two really nice graphs where you approach c from both sides and the function goes to something, all right? We start with that. Now here are all the laws. First one. The limit as x approaches c of k equals k. What? What is this? This is a law. This is saying that you can use this for the rest of the class, all right? That this is always true. Let me give you a specific example of this law in action. If I say, hey, what's the limit as x approaches, let's say 5, of the number 10? So we're approaching some value, and this right here is a number. Then you're saying, hey, look, what does 10 do as I let x go to 5? So what should the answer be? 10. And the reason it's 10 is because x is going to 5. But do you even see an x here? There's no x, right? So whatever x is doing has no impact on the number 10. So 10 is just going to stay 10. This is kind of trivial, but it's important that you understand the limit of a constant is just the constant itself. Nothing changes. All right? That's the first law. The second law, the limit as x approaches c of x equals, now you tell me what you think. If I tell you, hey, what happens to this if I let x go to c? What do you think this is going to go to? C, right? I mean, x is turning into c, right? So this x should go to c, and that's exactly what the limit law states. So a specific example of this would be limit, let's say x approaches 2 of x, that should be what? 2. So anytime we see that, if it's just x here, if x is approaching a number, then that's going to approach that. Okay. Next limit law. 3. Oops. All right, this is a nice one. Limit as x approaches c of f of x plus g of x equals the limit as, you don't have to write all these down if you don't want to, because they are in the book. But again, I want to be able to discuss them. That's why I'm writing them down. So what is this law saying? Equals L plus M. This law, got a big old hair on here. This law is saying that, what if you're taking the limit of two things that are being added together? Okay? So notice we have addition right here. Two things being added together, and I want to find out what the limit is. Then what I can do is I can take the limit of each one individually. You see how that's working? You're taking the limit of that one plus the limit of that one. And we already established in the beginning that this limit was L and this limit was M. So you're just going to add the two answers. So let's not overcomplicate it. If you have two functions separated by addition and you're trying to find the limit, you do them individually. All right?
So it would be c plus c, right?
Where?
On that one, the f of x. If x is leading to c.
Well, you don't know what this is, though. See, because in this law, this was x exactly, right? Here we're saying it's some function of x. It could be a lot of different, x squared plus 1. You know, we don't know what that is yet. Now, we do know it goes to L because we assumed that in the very beginning. Okay? So we can add. Now, property 4, there's just one change to property 4 from this one. What do you think it is? Subtraction. Subtract becomes subtract. Okay? All right, this next one, the fifth one, always seems to complicate or confuse people. All right, so there's the law, but let me just show you an example of this. What is the limit as x approaches 2 of 5x? All right. So if that was just x, right? If this was just x, then we would just plug in 2 for x, wouldn't we, using this rule? But we have a 5 sitting in front of it. So how does that 5 impact the answer? Well, according to this, if we have a number sitting in front of the function, then we can really just ignore the number, bring it out front, and then find the limit of what the function is. So this actually becomes 5 times the limit as x approaches 2 of x. And what did we say this would be? 2. So this would become 5 times 2, which is 10. So isn't that really like all you did was plug 2 in here and just got 10? Yeah. That's really what happened. I mean, that's what happens at the end of the day. So, but this law says we're allowed to bring that constant out. Y'all follow? Okay. 6. There's 8 of them. Sorry, I don't make this up, okay? 6. The limit as x approaches c of f of x times g of x. All right. This is, remember what happened when we took the limit and we had addition, we just added up the two limits, right? If we took the limit and we had subtraction, we just did the subtraction of both limits. What does your gut tell you would happen if you take the limit and you have a product? No, if we add two functions, then you just take the limits of them individually, right? And you add. If we subtract, you just subtract. So if we multiply, what do you think you do? Just multiply them. Look, do them individually. See, these laws are just saying that you're allowed to do this. That you're allowed to do it. Let me give you an example. What if we have limit x approaches 2 of, let's say, x squared times x plus 1. Okay? You see this? Do y'all see multiplication right here? According to this rule, if I have multiplication, then I can do the limits of each one of them separately. Right? I can do the limit of the first one and the limit of the second one. So I can do limit x approaches 2 of x squared, and then times limit as x approaches 2 of x plus 1. Now, I'd still have to go figure out what that is and figure out what that is, but the law says I'm allowed to split them up and just multiply the answers. Does this seem obvious, like you should be able to do this? Yes? Like, does it seem reasonable? Okay. We're going to find out later, we're going to do something called taking the derivative of something, and it turns out that when we have a product and we do this thing called taking the derivative, you cannot just do them individually, and it really creates kind of a mess for us. But for the limits, we're okay. We're allowed to do this. I'm just going to leave this as, we could continue on from there, but that's the property in action. All right, 7 has to do with division. What do you think the division is going to become? Yeah, you can divide them both, right? So the 7th property says if you were trying to take the limit and you have two functions being divided like this, that you are free to do the limit of the top one and then over the limit of the bottom one. Again, just look at this as me telling you that we have permission to do this in everything. You don't lose anything. Like, you're not breaking any rules. You can do them separately. And then the last one has to do with roots. If you take the limit, and let's say you have the nth root of a function. So let's say like you had the square root or cube root of a function. This law is actually pretty amazing. It allows you to take the limit and put it inside the root and do the limit of the function first, then at the end take the root afterwards. So it saves us some complications later on by being able to just look at what's inside here, figure out what it goes to, and then calculate the limit. All right, those are the limit laws. Let's see if I don't like the way they do that. But let's do a couple of examples using all of these now. So first example, if these first examples seem like straightforward and kind of like too easy, just bear with me. All right, they'll get a little more complicated. How about this? Limit x approaches, let's go -5 of 3x plus 1. All right, let's think about this. X is approaching -5, right? I have addition here, right? So I'm allowed to take the limit of each one of these individually. Now, I'm going to try and move kind of quick through this. So you just tell me if this is like too overload. All right. I could split this into two limits, couldn't I? With addition? But at the end of it, I'm just going to be doing the limit of each one individually. Can you tell me what the limit of that one would be as x goes to -5 of this right here? -15. Now, the reason you get that is because, well, I erased it, but we know the constant just comes out, right? And then you just let x go to -5, and then you multiply it times 3. So really, it's just like you're just plugging -5 in there, right? So we know we would get -15 there. And then plus, now, what happens as x goes to -5 of a constant? It stays the same, so plus 1. So all you get is -14. Doesn't it just seem like all of this stuff we're doing, and all you're doing is plugging in -5? Like, why are we going through all this? Just wait, because these are very basic functions. Let's do another example. How about this one? Limit x approaches 3 of x times x plus 2. What does this equal? What does your gut tell you here? 15? Yeah, because we have multiplication here, don't we? And if we have multiplication, we can do them each individually, can't we? And then we'll multiply the answers. So if we let x go to 3, that's going to be a 3 times, and then if we plug 3 in here, we're going to get 5, and then that's 15. So we're just plugging in, right? So why go through all this notation if all we're doing is plugging in, right? Doesn't it seem like a little bit of a waste of time? Just trying to confuse you more? A little bit? Let's do another one. How about this? Limit x goes to 1 of the square root of 10 minus x. Should be 3, right? Now, are we allowed to just take the limit of inside of here without taking into account the square root?
Yeah, but we could shift, rule 8 would shift the limit.
That's right. The rule 8 says that I can go in here and I can take the limit of what's in here. And if I just replace this x with 1, I get 9. And the square root of 9 is 3. So this is root 9, which is 3. So I think, is it safe to say that up to this point, like, we're not really doing anything other than plugging a number in? Like, big deal, right? So let's try something else. Okay? Try this one. Limit, one more nice one. You have division there, don't you? Can I do these individually?
Yes.
Yes, I had a property, it was what, 7, I believe?
Yeah.
7 said I could look at the top and bottom separately. Now if I look at the top, it's addition, so I can do these separately. And I let x go to 3, and this is just going to become, what? 3 plus 4, 7. So the top is headed to 7. Where's the bottom headed? 6, and your answer is 7/6. So all of these, we're getting nice answers, right? So don't lose sight of this fact. If you were to graph this function, do you all know what that would look like if we graphed it?
Yeah, like up 1 and then across. Over 3 up 1.
Yeah, that would be, I'm just trying to make sure you don't lose sight of what we're doing here. That thing in red that I circled, that's a line, has a y-intercept of 1, has a slope of 3. So it goes up 3 over 1. So it's like this, right? That's your line in that first one, right? What we've discovered is that if you approach -5, which would be like 1, 2, 3, 4, 5, -5, you go down the graph. If you were to approach this point from the left and from the right, what would it be headed towards? From the left and from the right?
-5.
No, we're approaching -5 on the x. This y value would be -14. From this direction and from this direction, our y coordinate would be -14. That's what we did last class, right? I gave you a picture and you told me the limits. Right here, we found the exact answer for this line without ever looking at it, right? And all we had to do is plug numbers in. This one, same thing. If we graph this, if I graph that function and we approach 3, we know we'd be headed towards 15. If we graph this function and I headed towards 1, from both sides it would be headed towards 3, with no picture, right? This one, this is a pretty ugly function actually if you graph this one, but if you approach 3 from both sides, it's going to be headed to 7/6, which is, some fraction, whatever. Make sense? But so far we have not run into any real big issues, and just plug in until we get to this one. Limit x approaches 3, x plus 4. Let's not do that one. Let's do x squared minus 9 over x minus 3. What's going to happen here? We can do it top and bottom, right, separately. So if we go in the top, we plug 3 in for x, what do we get? 0, right? So I'm going to put an arrow here, not an equal sign. I'm going to put an arrow. I'm going to put 0 here. On the bottom, 3 minus 3, again, is 0. We get 0 over 0, right? And this was what I was trying to get you to see when I first started talking about limits, that this is kind of what we're trying to be able to handle. We want to be able to handle 0 over 0. And do y'all remember what we call this? An indeterminate form. I know I said that in class. Anytime we get something like 0 over 0, it is referred to as an indeterminate form. And so, do we have an answer right now? We don't, right? We don't. I don't have an answer for this. I don't. I know there's something very bad happening at 3. Now, would there have been something bad happening if I said let x approach 2? What would it be on top? Would it be 4 minus 9 be negative 5 on top? And then 2 down here would give you like 2 minus 3 is negative 1. So you get an answer, wouldn't you? If I asked you to approach 5, you would get an answer. No problems. The only point that causes an issue is if I approach 3. But can we still figure out what's happening with this graph? Like if we go 1, 2, 3, like the graph is somewhere. We know that we get 0 over 0, so we know the graph has a hole. It's not defined. But that doesn't mean that it's not coming in from the left and right to something. Okay, it may still be coming in from the left and the right to a point. So how do we determine that? Well, when we see 0 over 0, when you see that from here on out, I want you to think a couple of things, all right? So when you see 0 over 0, I want you to say to yourself that this is bad, okay? That this is bad. And to fix it with algebra. The only hope we have right now of remedying this situation is to try and do some algebra. So let's go back to the original problem. Let's put it up here. Limit x approaches 3, x squared minus 9 over x minus 3. And I hope that some of you may have noticed that the numerator is something very special. You'll recognize the numerator when you were doing all your factoring techniques? So when I say algebra here, most of the time that means factoring in this case. So what is that numerator? We have a special name for that numerator. Difference of squares. Does that look familiar? So a difference of squares can factor. How would that numerator factor? X plus 3, x minus 3. Good. And is there anything nice about what just happened there if you factor the numerator like that? Yep. You can cancel that x minus 3 factor. See this right here? That cancels exactly with this, right? And so what you have now, the only thing left is x plus 3, right? And notice I just bring the limit with me, right? I cancel this algebraically and I get this. Now what happens if you let x go to 3 there?
9.
You're adding, right? 3 plus 3. So 6, right? So that means you have a value of 6. So that means if we were to graph this, this function, if we graphed it, then at 3 we would have a hole. Is that clear? But as we came in from the left and from the right, the y value would be approaching 6. Not necessarily ever getting to 6, but getting closer and closer. Right? All right, let's do another one where we have some difficult, not difficult, but some issues with the 0 over 0. So how about this? I'm sorry, I should probably move that out of the way. All right, how about this one? Limit x approaches negative 2 of x plus 2 squared over x squared minus 4. So what happens as x approaches negative 2? Let's take a look at the top. Negative 2 plus 2. 0 squared. 0. So the top is headed to 0, right? What about the bottom? You have negative 2, but you're squaring it, right? That means negative 2 times negative 2, which is positive 4. And then you're subtracting 4. So you get 0 again. So you have 0 over 0, don't you? So that means we have to do some sort of algebra. So do you see any algebra that you could do there?
Yeah.
What?
X plus 2 and x plus 2.
Okay, we could write the top as x plus 2 times x plus 2. Is that what you're saying?
Yeah.
And then what about the bottom?
X plus 2, x minus 2.
What is that you're doing? Difference of squares again, right? So you had difference of squares down here, which is this. And then the top, you just rewrote it as that times that, right? Okay, now what can we do?
Cancel out.
Cancel out.
X plus 2.
Just one of them, right? Okay.
But when I plug in negative 2 up on top, I'm going to end up with 0.
Okay, so if we plug in negative 2 up here now, what do we get? 0 on top, but what do we get on the bottom? Negative 4. Don't you? That's not 0 over 0. That's 0 over negative 4. And what is 0 divided by any number other than 0? 0 divided by any number other than 0 is 0. So your answer is 0. That means if we were to graph this, and if we were to be approaching negative 2, here's negative 2, the graph would be approaching from both sides what value? So the height, right, would be approaching 0. 0's here. So I know that I'm going to have a hole here because I'm undefined, right? I knew I was undefined at negative 2. I tried plugging in, I got undefined. But I know that from the left and from the right, it's approaching 0. Yes? You sure? Y'all are acting like my Cal 2 class this morning, like they were still asleep. So far, all I've used in order to do this is a little bit of factoring, right? Difference of squares. But we know how to use other factoring. Like we have other types of factoring. So let me give you another limit. Let's do limit x approaches 5. Let's go x squared. Let's go minus 6x plus 5 over x squared minus 3x minus 10. Hopefully I did that in my head, so hopefully this will work out. Yeah. All right. Okay? So first thing you always do with the limit is just try and plug the number in and see what you get, right? So don't ever get away from that. Trust me, on your test, I will give you a problem where you'll plug in and you'll get like 5 over 2. And that'll be the answer. But people get so into the habit of trying to factor things that they start factoring when you don't need to. So first plug in and let's just see what happens. 5 goes in here, square 5, what do we get? 25. So we have 25 and then minus 6 times 5 is 30 and then plus 5. So that's 0 on top. And on the bottom, we get 5 squares, 25 again, minus 3 times 5 is 15, and then minus 10, that's going to be 0 again. So we do get 0 over 0. This is bad, right? This is bad, and that means we need to do some algebra. Now these are quadratic trinomials. So we talked about, remember we were doing the review packet, things you should know how to do coming into this class, and we were doing the AC method. Now you have to do your AC method for each of these, and you've got to factor them out, which I'm not going to show the work for. I'm sorry. I mean, I'm willing, if you're willing to come by my office and I can help you on factoring, but getting through 1324, you should have done enough factoring there, and then here now you just have to be able to do it. Right? So it might take you a little time. You might have to do it on the side and figure it out, but is it all right if I assume that you can do that? So what does it become?
X minus 5.
X minus 5, x minus 1. That is a factorization of the numerator. And then the bottom?
X minus 5, x plus 2.
X minus 5, x plus 2. How'd you get so good at your factoring?
1324.
Okay. There. That's what it should take, right? You should be able to do that. Taking 1324, that should be within reason. Now, what at this point?
Cancel out the x minus 5.
Cancel out the x minus 5s. And see, do you realize that this is the part that's giving you the zeros? Right? X goes to 5, that's going to go to 0, that's going to go to 0. That means what's left won't go to 0. So what do we get? On top, plug in 5 into this one, you get 4, and then on the bottom, 5 here, you get 7. So it's approaching 4/7. So if we were able to graph this, and we approach 5, the y value would be approaching 4/7. Do you see how in the last few examples, what I'm doing is I'm actually finding kind of a workaround as to this 0 over 0? We're able to find a numerical answer, even though we know at 5, we're getting 0 over 0. But we know what it's approaching, right? And this all goes back to that whole picture I drew for you a long time ago with 2 points and me trying to find the slope of that line and me trying to drag this second point over and knowing that when we land this point on top of that point, we got 0 over 0. And we said, well, what do we do? Well, this is now how we're going to handle it. We're going to use something like this to handle that 0 over 0. All right. You all right? Okay. Just when things start to feel a little bit comfortable, we have something like this. So find the limit, this is an example, find the limit as x approaches 2 of f of x. Now, I haven't given you the function, right? So I'm going to give you the function over here. Let me tell you what the function is. F of x is equal to x squared minus 4 over x minus 2 if x is not equal to 2, and 5 if x equals to what? What is that? What is that? This has a name. These are called piecewise functions. Do y'all remember seeing that in 1324? Piecewise functions. Piecewise functions are functions that, basically the way piecewise functions work is that you have, maybe for a certain part of the graph, it's one function. And then after you get to a certain point, it switches over to some other function. And then maybe after a certain point, you have it switch over to another function. So you have these 3 pieces, right? Now, in the real world, and especially in business, piecewise functions are used all the time. Any of you pay utilities? How many of you pay for your own electricity? Okay. Electric bills, you get charged a certain rate for the first so many kilowatt hours you use. After you go over a certain amount, you start paying a higher rate. And if you go to another amount, you pay even more. So it's like, yes, we'll give you your electricity for pretty cheap, but if you use a lot of it, we're going to charge you more for the more you use. Same thing with water. So you fall into these different tiers depending on how much you use. So if you're just in a little 300 square foot apartment and your utility usage is going to be minimal, so you'll probably never see the second tier. But if you're in a 5,000 square foot home, you're maybe in the 4th tier of electric use, right? So you're going to be paying a lot more. Does that make sense? Those are piecewise functions. You pay a certain rate for a certain amount of time, then the rate goes up, and then the rate goes up, you know? And then that used to be this way for cell phones. You get like the first so many, remember, y'all probably don't remember when you used to have to pay for your minutes? Yeah. Right? So you get like your first so many minutes are free. Well, data's like this for a lot of carriers, right? So you have like, you get your so many free, and then after that, right? What's happening though, that's a function that acts a certain way for a certain amount of time, then after a certain amount of time, it changes to something else. These are piecewise functions, right? All right. So what in the world is this function doing? Okay. I'm not going to try and graph this at all. I want to know what this is, right? I want to know what that is. Now, when we say, what is the limit as x approaches 2? That means that we are letting x get close to 2, right? Without actually being 2. Do you agree? Let x get close to 2 without actually being 2. This function says, look, if you want to plug x in, here's what you do if x is not 2. And here's what you do if x is 2. So what if I want to plug it, like right now, if I ask you, everyone, what's f of 2? The answer is 5, right? Because we're plugging in 2, right? And what does it spit out? It spits out 5. But what if I say, what's f of 3? This time you plug that 3 into here, right? Because if I'm plugging in 3, 3 is not 2, so I go in here. Yeah? Was it 5? I didn't mean for that to happen. That's coincidental. That has nothing to do, these are not related. Okay? So the question is, when I'm taking this limit and I'm letting x approach 2, I'm plugging into top or bottom? If I'm asking for the limit as x approaches 2, am I plugging it into the top function or the bottom one? This x is approaching 2.
Oh, approaching anything but 2. So it's top.
That's right. So if you have to go back to when we were doing this on a number line. I said approaching from this side and this side, right? So if we come in from this side, you can give me an example of a number over here like 1.9, 1.99, right? Remember when we did that? So if I'm approaching 2, I'm not 2. I'm close to 2, but not 2. That means we have to be looking here. Yes? So if I'm here and I try and plug 2 into this, what do I get? What happens when I plug it in? So I may as well just take this and replace it. Limit, x approaches 2. I'm plugging into the top one, x squared minus 4 over x minus 2. And we're getting something that looks like 0 over 0, aren't we? And the only way to fix that is to hope that we can get it with some algebra. And we can, right? I did another difference of squares for you. X plus 2x minus 2 over x minus 2. The x minus 2's cancel. And what do you get? 4. So this is kind of an interesting graph. If you're not going to be asked to graph this, but here's what we did. We found out that if you go to 2 on this function, and if you plug 2 in, what do you get? If I ask you to plug 2 in, what do you get? You told me a second ago. 5, right? So at 2, I'm up here at 5. Agreed? Solid dot. But as we approach 2, where are we headed? We're headed to 4. So 4 is down here. So that means I put an open circle here, and I've got this picture. See, from the left I'm headed to 4, from the right I'm headed to 4, but at 2, I'm up at 5. All right, let's try a different one. You look thrilled. Let me tell you, you look thrilled. All right, for this one, I'm going to start by giving you the piecewise function. And I'm going to ask you for a couple of different things. All right, here we go. In this section, I think this is the most difficult thing for most people. Like the first few problems I gave you where you just plug in and nothing happens, that's great. Those others where you had to do a little factoring, students do pretty well with that. It's the piecewise ones that cause, I think, the most issue. So let's do this. How about do something kind of similar to your homework? How about 5 minus x, and let's go 5 plus x. And let's do this if x is greater than or equal to 3, and this if x is less than 3. So there's a piecewise function. Okay, so I'm giving this to you. This function is going to do this as long as the x you're plugging in is bigger than or equal to 3, and your function will do this if the x you plug in is less than 3. First problem, first question. Find f of 3. Do you see a limit here at all? Do you see a limit? Am I asking you for a limit? No. I just want you to plug 3 into this function. So if I plug in 3, am I going to be in the top or the bottom? Top, because this says you do this, right, if the x you're plugging in is bigger than or equal to 3. And we are plugging in 3, so we get 5 minus 3, which is going to be 2, right? So the function's value at 3 is 2. All right. Part B. Find f of 0. 5? So where did you plug that in? Plug it into the bottom one. Because I'm plugging in 0. 0 is less than 3, right? And if I plug in 0 here, I get 5 plus 0, which is 5. Okay, so nothing too crazy yet? All right, how about C? How about the limit as x approaches 3 from the left of this function?
So be the bottom one? It's less than 3.
Okay, good. So I'm asking for a one-sided limit here. I'm looking for the left-hand limit, right? So I want you to imagine what this is saying to you is, hey, look, we're supposed to be approaching 3 from the left, right? From this side. So an example of a number that would be over here would be like 2.9. Do you all agree with that? So I'm not actually going to plug 3 into this because 3 would put me up here, right? I'm approaching 3 from the left, so 2.9-ish. Would that put me here or here? Top or bottom? Bottom, because 2.9 is less than 3. So I'm actually going to be plugging it into this one. So this really means take the limit as x approaches 3 from the left of 5 plus x. I guess the critical part is for you to realize that I picked 5 plus x not because I just like flipped a coin, right? It was because I'm approaching 3 from the left that it forces me to be on this function. And now we just go back to what we just learned. Just try and plug 3 into this, and what do you get?
2.
Careful. Plugging in 3, that negative was only for which side you're on. So 8. Right?
Oh, okay.
Sure?
I see.
Yeah, be careful with this.
It was a negative,
Yeah.
but it's actually where it's coming from.
That's pretty common, is that students will look at that sign right there and think that that's the sign of the number here. But this is only to let you know which side you're approaching from. All right? What do you think I'm going to ask you in part D? The right-hand limit, right? So 3 plus of the function. So now we're approaching 3, but we have to approach with numbers that are a little bit bigger than 3, which forces me to the top or bottom. Top this time, right? Numbers bigger than or equal to 3 go to this one. So that means limit x approaches 3 from the right of the top function, 5 plus x, right? Wait, hold on, minus x, this is the top one. And what does that give me? 2. All right. Part E. Now I'm going to ask you what the limit is as you approach 3, and I'm not going to tell you which side. So I'm not going to put a plus or minus there. What do you think? Wouldn't it be what? What top one?
The 5 minus x is this
Oh,
greater than or equal to 3?
or does not exist. Okay, so look, let's look back. Look back. You have to think back, I guess. Think back to last class. We said that when you don't put plus or minus there, it's implied that it must be the same from both sides, right? For this limit to exist, they have to be coming into the same place from both sides. Now, are they? What's happening as we came in from the left? We got 8. What happened when we came in from the right? We got 2. Therefore, the only way this could be an answer, right, is if these were both 8 or both 2. But they're different. So we say does not exist, DNE. The limit does not exist. So when you don't see plus or minus, this is a very strong condition. It's saying that from the left and the right, you have to be the same. So it's kind of like that picture that I had earlier of that, right? From the left and from the left and the right, they're going to the same place, right? This limit would exist. But if you have something that looks like this, that limit wouldn't exist, would it? Because from the left it's headed here, and from the right it's headed there, different places. That's what we have here in this problem. We have a left limit and a right limit that are headed to different places. Questions on that? Okay. Let's try another one. Let's see. 120. We go till when? Okay, so what I'm going to try, I'm really trying to adapt to these hour 15-minute courses. I'm used to teaching hour 40-minute classes, and it's bothering me. I know for you it seems like 5 hours in here, but it just blows by way too fast for me. All right, let's try this one. X over x plus 3, if x is greater than 0, and x over x minus 3, if x is less than or equal to 0. First, a couple of preliminary questions. What's f of 3? So you're going to be in the top one, right? Because you're plugging in 3, which is bigger than 3. Or 3 is bigger than 3 now. 3 is bigger than 0, right? So you plug 3 in here and here. You get 3 over 3 plus 3, which is 3 over 6, which is a half, right? So at 3, you plug it in, you get 1/2. Do you see why you have to be real careful with that? Because what would happen if you plug 3 into the bottom one? You'd end up with 0 on the bottom, wouldn't you? On top wouldn't be 0, but it would be undefined, wouldn't it? So if you said, hey, the answer to this is undefined, you're not using the piecewise function correctly. All right, how about what is f of negative 3? What if I say plug negative 3 in? What do you get? So which one are you going to be in, the top or the bottom? We're going to be in the bottom one, right? So you got to be careful. If you plug in negative 3 right there, you can get 0. But because negative 3 is less than 0, we're going to go negative 3 over negative 3 minus 3, which is negative 3. And then hold on, don't tell me. Hold up. Negative 3, this is what we were talking about?
Yes,
remember that?
Negative 8.
6, there you go, okay? So 1/2. Negative divided by negative is positive, so 1/2. Okay. Again, kind of coincidental that these are the same answers. All right, let's talk about some limits now. What is the limit as x approaches 0 from the left of this function? Top or bottom?
Bottom.
Bottom, right? We're approaching 0 from the left, which means we're down here, right? Plug 0 in there. Now I'm actually going to write down the piece of the function we're plugging into. In case you have to look back at your notes, you'll know that we're using the bottom one, right? And what do you get there? 0 over negative 3, and that's okay? It's 0? All right, cool. What about if we approach 0 from the right? We're in the top function now, right? Because we're approaching 0, right, from the right-hand side, which means that we have to be just a little bit bigger than 0. If you need to, draw a little number line, put your 0. We're approaching from the right. We're a little bit bigger. You know, 0.001, something like that. So that puts us up here. And now plug in. And when you plug in, you get 0 over 3, which is still 0, right? What do you think I'm going to ask for part E? Both sides, right? And this time, you're going to have an answer, right? Because the left limit and the right limit are the same. And so you get an answer for part E, which is, what is the limit as x approaches 0 with no indication of left and right, which implies both? And the answer is 0. So if someone asks you for this limit right here, on a piecewise function, you've got to check both sides. You've got to go find them both and make sure they match. All right. One more of these, and I think I'm going to give you a few problems to work. How about x squared plus x if x is greater than -4 and sorry, I just want this, I kind of want this to work a certain way. You know what? Make that just 3x, not -3x. All right, you ready for some questions? All right, first thing, what's f of -4? So which one are you going to use? The bottom one, right? Because this says has the equal sign right there. So f of -4 is just going to be 3 times -4, which is -12, right? Let's say that's part A. Part B, let's do some limits. What's the limit as x approaches -4 from the left of the function? So the reason I wanted to show you this one is because you get some of these signs start to get messy here. We've got -4 is the number we're approaching, right? But we're approaching it from the left-hand side. So we've got all these weird negatives in here. So which function are we using, top or bottom? Bottom? Top?
No, it should be -4.
Okay, so let's see here. Here's -4, right? So we're approaching from the left. We're approaching from over here, right? So that means we are less than, right? Less than -4, which is to the left of it. Okay, that's what this means. X is to the left of, or smaller than -4. Okay, just want to make sure everyone's comfortable. Some people have trouble, like if this is 0, they for some reason think that this is smaller, I don't know. But this means we're on the left-hand side. So we're going to plug into the bottom function. Limit, x goes to -4 of the bottom function 3 times x, and that you just plug in, you get -12. So it looks like we've been getting, everything looks like the same answer, right? Plug in -4, you get -12. If you approach -4 from the left, you get